Hi everybody, Marty Geyer here, gsp295 again, and we're back to talk about graphs. So there's a couple different sections here, things to talk about, but firstly we're going to talk about the basic terminology. There's a lot of graph terminology, and we have to know what terms I'm throwing around here in order to understand any of the other algorithms and things that are based on graphs. So the simple stuff first. In a typical graph, like you have here, a vertex is simply a circled thing, usually graphically represented on the graph. It's also called a node. And between two vertices are an edge. Vertex and vertices is the plural. Between two vertices is an edge, which is represented by a line. And two vertices that are connected by an edge are called adjacent vertices. That's really quick basics. A vertex or a node, similar to a binary tree, can represent some piece of data. So usually you have in there some edge links going out, but then you also have some piece of data like a string or a user record or something like that. And we'll get into that when we get into the implementation specifics. So now you can have a whole bunch of different types of graphs. And let's continue talking about the terminology here. So a directed graph is this one here. Directed graph is basically a graph with arrows coming out of any particular vertex. And what that means is you can traverse, for example, in this case from C to A, but you can't traverse back to A to C because the arrow is only going this way. So it's singly pathed, which is called directed. And it's still possible, like in this case, that you can have B and C going back and forth. So you can go from B to C and C to B, but you have to draw two lines there to indicate that both directions are possible, because it's directed going this way and going that way. Undirected. Undirected is simply removing those lines so that you have, or removing those arrows rather, so you have simple lines connected. And what that means is you can traverse any which way, and it doesn't really matter which way you go. And so everything is assumed just to be a two-way connection, like it is in this case. That's kind of the common, simple way that we talk about graphs, but sometimes there are many cases in which traversing a path takes more time, space, etc. than going backwards. For example, if you jump down with gravity, then the time or the effort it takes to do that is relatively simple. But getting back up once you've jumped down from somewhere can be an enormous amount of effort. So if you were drawing a graph of those two states, for example, you wouldn't have one be the same number as the other. You'd rather have one be a higher number to represent that it's harder to go one way than it is to go the other. So with that, let's talk about weighted graphs back over here. So this is an example of a weighted graph. So weighted graphs are graphs, but with numbers attached to the particular links, or the edges, between the vertices. So in this case, A to C traversal costs 3 whatever, we don't know. But that's just a simple cost estimate. It could be distance, could be price, could be some other function that you create. So you can have weights on either undirected, as in this case, an undirected graph, or you can have them on a directed graph as well. Usually you see them more often in a directed graph because each particular direction costs something to traverse. So there's a couple other issues here, or terminology pieces to talk about. Connected. Connected, rather than tell you what connected is, I'm going to tell you what connected is not. This is an example of not connected. So a whole graph here, A, B, C, D, E, F, G, H. And this piece right down here is obviously not connected. So it is just like it sounds, the word connected, which means it's not connected to anything. Formally connected means that every vertex has a path to every other vertex. So because we can't get from A to H, it's not connected. If there was, however, you can still get from, say, A to F and A to E. That doesn't make it connected because not every pair of vertices is connected. However, you can pick apart connected into smaller pieces and say that this is weakly connected, and you can say that this subgraph of G and H is connected because these two nodes are connected. You can say the subgraph of this piece is also connected, and that's often done to indicate pieces of connectedness within unconnected graphs. We're generally not going to touch on, other than what I've just said, that's about all we're going to touch on with connected and unconnected, because unconnected isn't really helpful to us in determining algorithms to traverse a path because you can't get there at all. So it's not terribly important in terms of algorithm-wise, but you have to know it can exist, and you have to account for it when you're creating an algorithm, because you can't simply go, oh, well, that'll never occur. Sometimes it is possible that the distance between 2 points is infinite, in other words, or untraversable, or null, or however you want to indicate it. Let's see. So our old friend, a binary tree, here is an example of, oh, I'm sorry, let's go back in one more term, which is cyclic and acyclic. So in this graph up here again, we have a cycle. We can go from A to B, B to C, C to A. And now we've created a big loop, and that's called a cycle. And when you have cycles in a graph, it's a cyclic graph. But more often than not, we talk about when a graph doesn't have a cycle, and it's acyclic. So our old friend binary tree down here is a perfect example of an acyclic graph. You can always ever go down. I notice a lot of times we just, as a side point, we just draw lines on the binary trees. But that isn't entirely accurate because you can't traverse back up a tree, right? So technically, a tree has directed length, which makes a tree a directed acyclic graph. And that's important to know, mostly because I'm sure it'll be on a quiz or a final somewhere. It always is. So having this as directional, and also there's no way to get back up the tree, so there's no cycle. Whereas in this case, if you were to think of this as a tree coming down from A and B to C, C goes back up to A, so there is a way to go back up. And there's I think at least 10 or 15 more terms associated with graphs, but those are the basics, and those are generally what we're going to cover here. Let's see, complete is the last piece. So this graph back over here again is a complete graph. Complete means that there are edges between every possible 2 sets of vertices, between every set of vertices, or between a vertice and every other vertex. Sorry, that's the formal way to define it. So A has to have an edge between itself and every other vertex in this graph. So let's check. So A goes to B, A goes to C, A goes to B, and that one is connected to everything. C goes to A, C goes to B, C goes to D, D to A, D to C, D to B, and B to C, B to A, B to D. So all vertices are connected to every other vertex, and that means that it's complete. That's a special term. Now, you'll notice if you draw out, and I encourage you to do so, a couple complete graphs, that they're usually geometric shapes that you're familiar with. So a 3-vertex complete graph is a triangle, because every node is connected to every other. This one comes out to be a rectangle. If you do 5 and 6, you'll see them form nice geometric shapes, pentagons and hexagons, etc. So they're usually pretty identifiable, but maybe not, because you can always draw the edges and the nodes differently. You don't have to draw D here, you can draw it over here and put lines around. So you can be fooled with the graphing of these things, but the definitions are important, that every vertex is connected by every edge, or by a edge. Let's see, I think that is all the graph terminology. I'm going to pause for a second and talk about the graph ADT.